All right, so we're going to finish looking at our graphs of tangent, cotangent, secant, and cosecant. And we're going to use what we know about sine and cosine to figure out what tangent looks like. Okay, a couple of weeks ago we had an identity, and we said tangent can be written as one trig function divided by another trig function. Does anybody remember how you can write tangent? Yeah?
1 over cotangent.
Okay, yep, that is one way to do it. You can do 1 over cotangent, but I'm looking for the other way.
Sine over cosine.
You can write it as sine over cosine. The only reason I'm going to do it this way is because we know a lot about sine and cosine. Okay. So here's basically what sine looks like. Okay, just the basic sine function. And here's cosine. All right, so let's make a graph. Just to have a general idea. Big ideas I want to know here is where it crosses 0, where it hits its highest values and lowest values. Okay, just a quick sketch. So, first thing I want to figure out is when tangent would equal 0. Right? And let's focus on this right-hand side. So asking when tangent equals 0 is basically asking when does sine over cosine equal 0. Okay, even simpler way to say it, when does a fraction equal 0?
In the bottom.
Careful, no, not in the bottom. If the bottom is 0, that's something else we're going to talk about. That's undefined. But when the top is 0. So if you can make the top of this fraction 0, you would make tangent equal to 0. All right, so tangent is 0 whenever sine is 0. Right. So can somebody give me a couple values where sine is equal to 0?
Zero.
Yeah, that's 0. Yeah, in the sine function. Where else is sine equal to 0? Pi. And 2 pi. And we keep going. Basically, any multiple of pi. 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. It just keeps equaling 0. Okay, we'll just do a couple. Now, Upi mentioned something else about the denominator being 0. Well, when the denominator is 0, that's when we get a discontinuity. Okay, that's when we get either a hole in the graph. In this case, we're not going to get a hole. The only time you get a hole is if the top and bottom have a common factor. The top and bottom are different here. Okay, so if the bottom is 0, we're going to get a vertical asymptote. Right, so that right there tells us this graph is going to look a lot different than sine and cosine. Okay, it is not a connected function. Okay, there are asymptotes. Somebody give me some values when cosine would equal 0.
Pi over 2.
Yep, pi over 2. 3 pi over 2. 5 pi over 2. 7 pi over 2. Basically every odd multiple of pi over 2. Right, and we could also go backwards. If you wanted, you could write negative pi over 2, negative 3 pi over 2. Negative multiples are still odd multiples of pi over 2. Right, and then if we know where it crosses the x-axis, if we know where the asymptotes are, we can use our calculator to check a point on each side of the asymptote. So like, let's say we had an asymptote, I'm just going to make up an easy number, 4. Okay, a good value to check in your table would be 3.99, something just before it, and 4.01, something just after it. You guys remember doing that? Graphing and checking before and after? Okay. All right, so let's see if we can graph tangent. I'm going to draw my vertical asymptotes first. Okay, so I have vertical asymptotes at, I'm not going to draw them all, but I'll put negative pi over 2, pi over 2, 3 pi over 2. Okay, next, I know it's going to cross the x-axis at 0, pi, and 2 pi. Right, so let's just sketch this one. Okay, basically, each section between the asymptotes is going to look identical. So if I can sketch what it looks like between one pair of asymptotes, it's going to look the same between every pair. All right, now let's just check some values right after pi over 2 and right before 3 pi over 2. So let's graph tangent. Okay, and I'm in radians. All right, pi over 2 is about 1.57. Okay, if you type it in, that's a good number to know. Okay, 1.57. So what's a value just after pi over 2? 1.58. Okay, notice at 1.58, we're down at negative 100 something. Okay, so we're way down. All right. 3 pi, if you do that on your calculator, 3 times pi and then divide by 2, it's about 4.71. Okay, again, that's 2 good numbers to know. What's a value just before 4.71? Sure, 4.7. Okay, and in that case, we're way up at positive 80. All right, so basically, our graph has to go through all these points. It has to be a smooth curve, and it's going to look something like this. That's the graph of tangent. Okay, now, this is the graph of tangent, but what we've done with this window, whatever the window is we've broken the period in half. You've got half a period here, half a period here, and a full period here. All right, if I was asking you to show 2 periods, I'd rather you not show a half and then a whole. I'd rather see 2 nice connected.
So should we change the x on that?
Yeah, we would talk about how we'll do that. Okay, so this is a nice graph right here that shows 2 periods. Okay, 2 nice periods. Right, so if I wanted to show exactly what I'm showing on the screen right now, I could set my x min at negative pi over 2. Okay, I'm just looking at that asymptote right here. And then set my x max at 3 pi over 2. Now the y min and y max, well, tangent goes up and down forever. So it doesn't really matter what you set that at. Okay, now this graph on the calculator is showing you exactly what I'm showing on that screen. Okay, on my calculator, I think I'm zoomed in a little more. I'm only going negative 4 to 4. On here, it's a little bigger. It's like negative 5 to 5 or something. Okay. Okay. So, any questions on the graph of tangent?
Did you find your asymptotes?
The asymptotes are whenever cosine is equal to 0, because that's in the bottom. So cosine is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, any odd multiple of pi over 2, including negatives. Yep. All right, now for cotangent, I'm not going to go through all the same stuff. Just wanted you to see one important thing. What's the difference between this fraction and this fraction? Yeah, they just flipped. Okay, so basically what's going to happen if we flip it, everywhere we had a vertical asymptote before, that's now going to become a what? A 0. And everywhere we had a 0, that's going to become no. The vertical asymptotes are going to become zeros, and the zeros are going to become vertical asymptotes because we're flipping sine and cosine. So now sine is in the bottom, and cosine is in the top. Okay, so the graph that we get looks something like that for cotangent. It's similar, but it curves the other way. Okay, and notice here, pi is an asymptote. Before, pi was a 0. On this one, pi over 2 is an asymptote. On this one, pi over 2 is a 0. So it's all the zeros and asymptotes switch places because you're switching sine and cosine. You flipped it. Now, how could I type this in if I wanted to graph cotangent? And Dalton mentioned a good way earlier. Do you remember Dalton? Yeah, you could type it in as 1 over tangent. All right, so if you type 1 over tangent, hit graph. Okay, again, the way my window is set, it's breaking it up not in the best way. But this curve that's right here, that's the red curve I showed in my graph. Okay, so any questions on the picture of cotangent? All right. So you might have noticed if you look at either graph, we got a 0 at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. How often are we getting zeros? Every what?
Every pi.
Every pi. Not every 2 pi. Okay, every pi. So the period of tangent and cotangent is pi. Okay, it naturally has a shorter period than sine and cosine. Okay. What's the period of sine and cosine? Yeah, 2 pi. And then the period of tangent and cotangent is just pi. Okay, it's a little shorter naturally. Right, so what that means is if I take, I'll show you an example. If I take the tangent of, I could pick anything, 2. Okay, that's what I get. If I take the tangent of 2 plus pi, I get the same thing. If I take the tangent of 2 plus 4 pi, same thing. Okay? What's happening here is we're getting the same values because pretend like you just put a horizontal line on this graph. And you look at where it hits a certain value. Well, it's going to hit a value here. It's going to hit the same value here. It's going to hit the same value again down here. It's going to hit it again down here. What's the distance between all these values? Pi. Each time you're just plussing pi. So when I just did this on the calculator, just think of it as me going down 2 periods, 3 periods, 4 periods, and getting to the same value just further down. Okay? I can also go the other way. I could go tangent minus 5 pi. Oop, I got to put in a 2. Okay. Now I'm looking at the same value. I'm just going backwards 5 periods. Okay. And the same idea works with cotangent. Okay. As long as you add integer multiples of pi, you can add 10 pi, 70 pi, 364 pi, guaranteed you'd get the same answer. But you can't add 1.7 pi. 1.7, that's not a period. Okay, you've got to move in multiples of the period. Okay, we studied that same idea with sine and cosine, except instead of a pi here, it was a 2 pi. Okay, you can do the exact same thing. If they gave you a problem in degrees, what would pi become? It'd be 180. So if you had your calculator in degrees, if you took the tangent of, I don't know, 5 degrees, and then the tangent of that plus 180, it'd come out the same. If you add 180 again, it'll still come out the same. Okay, you're just moving down the graph. All right, so we've learned our transformations many, many times, so I'm not going to go into as much depth here. But the basic idea is that every transformation for tangent, cotangent, it's exactly the same. Okay, there's no difference. A is a phase shift. B is a period change. C is your amplitude change, or vertical stretch, you can also call it that. And D is a vertical shift. Okay, so we had the exact same equation, I think it was yesterday. I just had the word sine instead of tangent, or cosine. All right, so I would just copy down this. That's all you really need to know. Okay, any questions on this equation? Yep.
What does the A and represent?
What's the A?
N.
What's the N?
A N. C plus A.
So this is your vertical stretch, your period change, your phase shift, and your vertical shift. Is that?
Yeah. Right.
Okay. All right, so just like we did with sine and cosine,
You go back.
we can find the period. Well, we can also do that with tangent, except with tangent, we don't use the formula 2 pi over b. Okay? We just use the formula pi over b. So the only time you use the formula pi over b is with tangent and cotangent. All right, so now we're going to get into doing some sketches. We're not going to be sketching these by hand, but we still need to know a little bit, even if we're going to sketch it on the calculator. Okay? We have to know where asymptotes are, and that's going to help us set our window. So normally, tangent has an asymptote, and I'm just going to do it in degrees to make what I'm about to say seem a little easier, but we wrote it as pi over 2. Okay, so normally, that's where your first asymptote is for tangent. Well, if we do a transformation, we're going to change where that asymptote is. Okay? It's not going to be at pi over 2 anymore. We might move it left, we might move it right. Okay? And we gotta know where we're moving it to. Right. So how you figure out where your asymptote moves is you take your argument. Okay, so in this case, that is my argument, 2x. You set that argument equal to 90. Okay? Or if you want to do it in radians, I'll write both, pi over 2. Right, so my first step on this problem, take my argument, it's 2x, set it equal to what the asymptote used to be. Okay, it used to be pi over 2. And now solve for x. Okay, when we solve this equation for x, it's going to tell me where my new asymptote is.
That's a 2x, right?
2x. Right. So you take your argument, set it equal to where the asymptote used to be, and for tangent, it's always pi over 2. For cotangent, it's different. Okay, it's at 0. You got to go back. If you're not sure, I would go back and look at your sketch. Okay, and then if we can find one asymptote, and we know the length of the period, we know that that asymptote is going to reoccur every period. Okay, so we just find the starting asymptote, and then from there we can go left and right and sketch as many periods as we want. Okay, generally, we'll read the directions and sketch however many periods they ask for. Okay, but it's just going to be on the calculator, not by hand. All right, so I took my argument, which was 2x, set it equal to the first asymptote for tangent, which happens to be 90, and now I need to solve. What would I do on both sides to get x by itself here?
Divide by 2.
Yeah, divide by 2, which is the same as multiplying by half. Yep. So where is my asymptote now?
Pi over 4.
Pi over 4. Okay, so I definitely know I'm going to have an asymptote now at pi over 4. Right? What is my period? Or just tell me the formula for how I find it.
Pi over 2.
Pi over b. What's b in this case? 2. That's my period. So what the period tells me is how often this asymptote is going to repeat. So I'm going to get an asymptote at pi over 4. The next one is going to be at pi over 4 plus the period. The next one is going to be plus the period again, plus the period again. You could keep adding the period. Okay, so any questions on what we have so far? All right, so for tangent and cotangent, let's look at the picture. An asymptote is a good place to start the graph. Okay, that's a good place for a x min. Because if you put your x min right on an asymptote, you're not going to chop this period into 2 pieces. Okay, so make your x min any one of these green lines. Okay, so make your x min an asymptote. Where do we know we have an asymptote? Definitely. Pi divided by 4. Okay, we just found that's an asymptote. So I'm going to make that my x min. All right, so let's make that pi divided by 4. And now they want me to graph 3 periods. All right? So I've got to think of it visually. Imagine you have a number line. Pi over 4 is right here. How long is each period? It's pi over 2. So if I went down pi over 2 to that point, how many periods would that window show me? 1. If I went down pi over 2 again, how many periods would that window show me? 2. Well, I'm going to go down one more time. How many periods would that window show me? 3. All right. So now I just have to type that in on my calculator. So for my x max, I'm going to start at pi over 4. And what am I really adding? 3 pi over 2's. Okay, you're adding it 3 times to get 3 periods. So I'm not even going to worry about what the decimal is. The calculator will figure it out. So I'm starting at pi over 4, and I'm going to go down from that spot 3 periods. That's it. Okay. Any question on how I just got my x min and x max? Okay, and that could change. Maybe they don't want you to show 3 periods all the time. They might ask for 2 periods or 1 period. Okay, depends on the problem. And now type in tangent 2x. Tangent 2x. Okay, and if we've done this right, we should see exactly 3 periods without chopping anything off. That's good. Okay, any questions on how we did that? Yeah?
I'm getting about 6 of them.
All right, so as long as you've got tangent 2x, and that's your window and you're in radians, you should be You should be getting 3. You got it? Okay. Okay, what I'm going to do is, just going to put this down here. On the test, you wouldn't have to write decimals if I asked you. You could just say your x min is pi over 4. And my x max, what did we say this was? We added how much? We added 3 pi over 2. Okay. I could add those up if I wanted by hand. That's going to be 7 pi over 4, which is the decimal 5.5. Right, so any question on that? Okay, it takes a little practice to get used to, but we'll try a couple. Okay, this one, I just want you to identify, one of these is the graph of 2 tangent x, one of them is the graph of 5 tangent x. Okay, I just want to identify which one is which. Okay, anybody have a thought? Which one is 2 tangent x? Kyle?
2 tangent x is more on the left because from what I see on like upper lines, it starts at like -1 and it'll go to +1 going to 0, so it's 2 points. And like the line's less curvy.
The curve, yeah, the curvy thing is what you really want to focus on. Okay, that's what's going to help you figure it out. What's the transformation that's happening here?
Period.
No, not. Yeah, we're doing an amplitude change or a vertical stretch. What happens if you have something that's curved and you stretch it out? It gets straighter. And the more you stretch it, the straighter it gets. So, which one is which here? 5 tangent x is what's on the left. Yep. Okay, because that one is stretched out more. It's straighter. Yeah. On the one on the right is 2 tangent x. Okay, so the straighter tangent starts to look, the more you've stretched it. Okay? Any questions on that? All right, so the last 2 graphs we're going to look at are secant and cosecant. For these, I'm just going to show you what they look like. We're not going to go into all the reasoning why. But if you wanted to think about why do these have asymptotes where they do, you would think about it this way. Secant is really 1 over cosine. Cosecant is 1 over sine. Think about the graph of cosine and think about where it hits 0. That's why I have asymptotes where I do. Okay. But without getting into a lot of depth about it, these are your graphs of secant and cosecant. Right, so you get these kind of U shapes and N shapes. This right here, what I'm putting a box around, that is 1 period. Okay? 1 complete U shape, 1 complete N shape is 1 period. And how many asymptotes do we get per period? 2. Okay, we've got the one that's to the left of the U shape and the one that's to the left of the N shape. And then this is starting a new period right there. That's to the left of this U shape. And then that asymptote is to the left of that N shape, which is cut off. Okay, if you're looking at cosecant, this is 1 period. How many asymptotes per period here? 2. Again, this one right here is part of the next period. Now, technically, I could slide this down and say, oh, that's a graph of 1 period as well. You've got full U shape, half an N shape, and then the other half of the N shape on the other side. But do you think that's a good way to display it? No. Okay, when I ask you to display it, I'd like it displayed one full U, one full N. Okay? Not a half and a half on each side of the screen. Okay. Are these continuous or discontinuous functions? Yeah, very discontinuous. You definitely can't draw this without lifting your pencil and starting at a new spot. All right, so let's see if we can just look at the graph of secant and find the domain, range, period, and asymptotes. It's kind of like what we did for sine and cosine. All right, let's start with the period. Right, so for secant and cosecant, these functions are more similar to sine and cosine. Okay, so to find their period, you're going to use the formula we used yesterday. 2 pi over b. Okay, so sine, cosine, secant, and cosecant all use this formula. Tangent and cotangent use pi over b. All right, so let's see. In this case, what number is in front of x? 1. Okay, there's a 1 in front of x. So what's the period of secant x? 2 pi. Okay, it's 2 pi over b, or in this case, 2 pi over 1. Any question on the period? That's the easy one. All right, let's look at the range. Okay, might have to zoom in a little bit. Look at that U shape. What's the lowest it looks like that U shape goes? 1. Yeah, goes as low as 1. And how high does that N shape go? -1, exactly. It's kind of tied in with sine and cosine, that 1 and -1, except instead of being between 1 and -1, it's always outside of 1 and -1. Bless you. So how would I write the range? Negative what?
-1 to 0.
Nope, it's actually never going to be between -1 and 0.
-1 to 0.
Tommy?
You could say all reals other than -1 to 1, or do you want with the parentheses?
You could say it's every real number except anything between -1 and 1. I didn't think of it that way, but that's fine.
You could do
Yep.
parenthesis with 1 to infinity,
Okay, that would cover the top part,
and then
One, two.
-1 with a parenthesis to negative.
and that would cover the bottom part.
Yeah.
Yep. So your range is -infinity up to, and it does include, -1. Okay, so that's everything up to right there. And then from 1 to positive infinity. And it does hit 1. All right, so that one, not too bad. Okay, the asymptotes. Okay. Well, we've got 2 different asymptotes. Okay, we've got, let's call this one asymptote 1, and that one asymptote 2. All right. Looking at that graph, how often does asymptote 1 repeat itself? It's here, and then it's here.
Everyone period.
Every what?
Everyone period.
Every 1 period. And what's the period of secant?
Or 2 pi.
2 pi. Right? So asymptote 1 repeats itself every period, 1 time per period. Okay? So the first time that it occurs, okay, is negative. Well, we could just graph it if you're not sure and try it, but I'm going to tell you it's at negative
2 to 2.
pi over 2. Okay, it's at negative pi over 2. All right, so that's one asymptote. And it keeps repeating every period. So the way you write that is like this. You're going to get an asymptote at negative pi over 2 plus any multiple you want of the period. Okay. This is the period. It's going to be in the next period. It's going to be in the next one after that, next one after that. It's going to keep repeating.
So one more time, how'd you get negative pi over 2?
All right, so we get, let's go back. Well, I know this is 0.
Yep.
Okay, and I just know that, let's see. Let me just graph it. That'll be easier.
Okay. So, because it goes 0, pi over 2.
Yeah. Let me graph 1 divided by cosine. All right, and I'm going to do zoom 7. All right, so whenever you're trying to find asymptotes, numbers you could always try on your own. Try pi. Try pi over 2. Try 0. You're going to have an asymptote at one of those kinds of numbers. Well, if I try 0, no. At 0, I'm at 1. Okay. So let me try the next one over. Let's try negative pi over 2. Let's try negative pi divided by 2. See how when I did that, it says there's no y value? That means it's undefined. If I did that in the table, it would say error. Okay? So to find your asymptote, try 0, try negative pi over 2, try positive pi over 2, try pi. Guarantee you're going to find one of those as an asymptote. It's not going to be something strange, like negative pi over 2 plus 0.6. Okay, I'm not going to give you anything like that. All right. So now we have where asymptote 1 is occurring. Where's asymptote 2? Yeah, that's symmetrical. It's on the other side. That's positive pi over 2. Okay. If you're not sure, take your calculator and just try it. So we have an asymptote at pi over 2. And how often does that asymptote repeat? Every Matt? Yeah, that one's also going to repeat every period. It's going to occur here, here, right? All the way down. Right? So now we get that asymptote repeating every 2 pi. And the reason I put n is because it just doesn't have to go down 1 period. It could go down a 4 pi, or 6 pi, or 8 pi, or 10 pi. I can keep adding multiples of the period, and it repeats forever. Okay, the asymptotes are the hardest things to get. Oh, those are tricky. But once we have those, the domain is very easy. Okay. What's the domain? It's everything except what?
Negative 1, 1.
So our domain, we're looking at the x values we can use.
Everything but
Everything but the
the asymptote.
asymptotes. Yeah, so we can just write that. Okay, domain, all reals, except, and you could either draw an arrow pointing to your asymptotes, or just write it in, all reals, except for the asymptotes.
So you wouldn't want a number value for that, all reals except asymptotes?
Yeah, or you could say all reals except, and then you could point down to your asymptotes. Okay, I think secant and cosecant are tricky because you don't just get one asymptote per period, you get two. Okay? Now, I could technically take both of these and combine them into one statement. We're not going to do that. We're just going to leave them as separate asymptotes. So if you look or check your answers like online or in the book, they're not going to exactly match what we're doing, but that's fine. This is acceptable on the test. All right, so now we did secant. Cosecant should be a lot easier, and it's very similar. Okay, domain, let's hold off on that till we know our asymptotes. Range, period, asymptotes. Okay, so now look at the graph on the right. What do you think out of those four things I just wrote is the same between these two? Range is the same? Yep. That one, the negative one. What else is the same? Period. Okay, period is exactly the same. So those two, just copy down exactly what you had before. 2 pi, negative infinity to negative 1, 1 to infinity. Okay, asymptotes. Let's go back and look at the picture. Okay, how many asymptotes per period here? 2 again. This one and this one.
So would those not have the same asymptotes?
Nope, these asymptotes are a little different. Okay, where's asymptote 1? That's actually at an easy spot.
Origin.
It goes through the origin, but that's which axis? Yeah, it's the y-axis. So we have a y-asymptote at 0. Yeah. Okay, that's where asymptote number 1 is. 0. And how often does that asymptote repeat? You're going to get one of them every period. That's our first one. And the second one, you can almost just look at it and say, well, I know this box goes from 0 to 2 pi. This asymptote is right in the middle.
1. I would probably 2 pi.
So this asymptote is at 0. This is at 2 pi. Pi over 2 would be right here.
Oh, 3 pi.
No, 3 pi over 2 would be over here.
3 pi over 2.
Pi. Okay, if you got an asymptote at 0 and you have one at 2 pi, pi is right in the middle of 0 and 2 pi. If you don't see it on this picture, you can always graph it, plus pi, and see if it says it's undefined. But it will be. Okay, so that asymptote is at pi. Okay, and that is going to repeat every period. Okay, so again, secant and cosecant, they are a little harder. They're not as easy as like sine and cosine. And now, what's my domain?
Everything but the asymptote.
Everything except those. All reals except asymptotes. Okay, on the test, there's only going to be one question that asks you domain, range, period, and asymptotes. Okay, all 4 like this. Okay, because these are time consuming.
Big question.
What's that?
So that was a big question.
Yeah. But 2 of the things are pretty easy, and I'm going to grade it. You can get one, if this is a 4-point problem, you can get each part separately correct. So just because you get one thing wrong doesn't mean you're going to get everything wrong. Yeah.
So we don't need to know, I'm not sure how to explain it, original table thing.
No, you don't need original tables. We're not sketching these by hand.
Okay, so
Yeah.
there won't be any of
No.
define shift or
No.
anything like that.
No, you're not going to have to sketch any of these graphs by hand. Anything I ask you to do with these is on your calculator. Yep. Because they are a little harder. Even with the calculator, it's still still a little harder. All right, let's, you know what, for this one, let's just find the period. Don't worry about the asymptotes. Let's just find the period, and let's graph it on the calculator. Yeah, the period is 2 pi, because we're using cosecant
2 pi over 3.
over 3. Right. So if I want to type cosecant in, which trig function do I flip to do that? 1 over sine. That's how you have to type in what I have right there. Right. And what would be a window that would, well actually, how wide does my window have to be to show 2 periods?
Double your period.
Double that. Okay, if my window was this wide, it would show 1 period. So let's make it 2 periods, which is,
Or we just double our point, or we would call it times 2.
someone just said it.
4 pi over 3.
Yeah, make it 4 pi over 3. Okay, if they wanted you to show 2 periods, you got to double the period. So let's try starting at 0 and go to 4 pi over 3. There's a complete U shape, N shape, U shape, N shape. That's perfect. That's 2 periods. Okay, that's all I want to do for that one. So on the test, I'm just going to ask for your window. All right, so summary of the periods. Okay, you already have this down. I'm just summarizing it. If you want to find the period of sine, cosine, cosecant, or secant, you use 2 pi over b. Only time you use pi over b is with tangent and cotangent. Okay, I put absolute value just in case b is negative, because we always want to use the positive. But I don't think I've given you a negative in any problem yet, and I won't be on the test. Okay, b will always be positive. All right, so we'll just we'll finish up by just doing a few more intersections, okay, on the calculator. Okay, just in case people that weren't here yesterday weren't sure how to do that. Okay, so we'll kind of review it, but I'll use some tangents and other functions. All right, what did we say yesterday with a trig function? If you find one solution, that really means there's how many? Think about like a sine wave and a horizontal line. If it hits it once, it hits it how many times? How many? Infinite, right? So if I start to draw a horizontal line and it hits it one time, it's going to keep hitting it infinitely many times. Okay? So the point when you're solving trig equations, if you can find one solution, then there's really infinitely many solutions. Okay? And the way that you write your answer is exactly what we did when we did the asymptotes. What you have to do is find one solution. Second, calc, intersect. Okay? Find one. And then put plus your period, which could be 2 pi. A lot of times it's 2 pi or pi times n. Right? That's how we represent this solution repeating forever. All right? So to do this, this is your second calc intersect. Okay, so second calc intersect. Find your solutions in one period, and then for each solution, tell me that it's going to keep repeating forever. All right, so let's try this one. Okay, there's not going to be anything to show here by hand. Everything is done on the calculator. Okay, how do we type in cosecant? 1 over sine. Yep. It's 1 over sine. And I want to know where it's going to hit what? Negative 1.6. Okay, now I have to find all the solutions within one period. That's all I want to focus on. So what is the period of cosecant? 2 pi. Yep, or 2 pi over 1. Okay, so what I'm going to do is just look at a window that's one period. I'll find all the solutions here first. Okay, so there's one nice period. And how many solutions do I get in one period? 2. The first solution, find it, is 3.82. Okay, second solution. Let's see. Is 5.61. And how often are these two solutions going to keep repeating? Every what?
Every period.
Every period. And what's the period? 2 pi. So put your period times n. That's how you say it repeats forever. All right. I'm going to skip the last one. It's the same idea. You graph tangent x and y1. Graph 2.5 and y2. See where they cross. But for tangent, how often would the answer repeat? It's every period, but what's the period for tangent? Pi. So find where they cross. Put that number right here. But just remember, it's pi n for tangent, not 2 pi n. All right, so if we need to, tomorrow we can go over some of these, practice them before the test. I'll also be here after school today. Okay, if anybody needs extra help.
Can you change the left side back to the one before that?
Yep. 1 second.
Yeah.
Does anybody need to copy what's here right now? Yep. Okay, so page 352, it says 3, 6, 7 through 10, 13, 15, 20, 28, 29, 31, 34, and 46 to 48.